You've scanned thousands of these. A menu, a ticket, a payment. But have you ever looked at the little squares and wondered what's actually written in there? By the end of this, you have built the encoder that makes 1 from nothing in pure Python, and your phone will scan the one we make. A QR code isn't random noise. The 3 big squares are finder patterns. They let a camera find the code and work out its orientation from any angle. Thin dotted lines time the grid. A strip near the corners stores the settings. Everything else is your data, plus its safety net. First, we turn text into bits. To encode any URL, we use byte-mode, a short tag that says byte-mode, then the length, then the bytes themselves. A version has a fixed capacity, so if our message is short, we fill the rest with a terminator and a repeating pad. Every decoder on Earth agrees on those values. Here's the clever part. You can cover a chunk of a QR code and it still scans. That's not luck. We deliberately add redundant data, error correction, so the decoder can lose pieces and rebuild them. The technique is Reed-Solomon, the same idea used on CDs and in deep space. Reed-Solomon does its maths in a finite field, a number system with exactly 256 values, where adding, multiplying, and dividing always land back inside the set. We need that so the algebra has no rough edges. It sounds exotic, and it is 2 lookup tables. We build those tables once. Starting from 1, we keep multiplying by 2 inside the field, and that single sequence visits every value. Logs turn multiplication into addition, so multiplying 2 field elements becomes lookup, add, lookup. That's the whole engine. Reed-Solomon treats our data as a polynomial. To protect it, we need a special divisor, the generator, built from the field. We divide our message by it and keep the remainder. Those remainder bytes are the error correction codewords, and they're what let a damaged code heal itself. Here they are for real. 28 bytes of data and 16 more of pure safety net computed by the code we just wrote. Those 16 are what survive a scratch. For a small code like ours, that data is a single block. Bigger codes split it into several, each with its own safety net, then weave them together. Because in the real world, damage comes in clumps, and interleaving spreads one clump across many blocks, so no single block takes a fatal hit. Before any data goes in, we draw the fixed parts, the 3 finder squares, their quiet borders, the timing lines, an alignment square, and one stubborn module that's always dark. These never change. They are the landmarks the scanner locks onto. The data fills the grid in a zigzag, 2 columns at a time, climbing, then descending, skipping every fixed pattern and the timing line. It looks strange, but it keeps related bits physically close, which helps the error correction do its job. A raw grid can come out with huge blank regions, or worse, accidental shapes that look like finder patterns and confuse the camera. So, the standard defines 8 masks, 8 ways to flip a regular set of modules, and we have to try all 8. We score each mask grid with 4 penalty rules: long runs, blocky areas, fake finder shapes, and too much dark overall. The lowest score wins. This isn't cosmetic. A good mask is the difference between a code that scans instantly and one that doesn't. One last piece. The decoder needs to know which error level and which mask we used. So we write that into the format strip, and we protect it too, with its own small error correction and a fixed scramble. We place it twice, so even a damaged corner can still be read. That's the whole encoder. We build the matrix, and to prove it's real, not just plausible, we compare it module for module against a reference library. Identical. Then, the final test, a phone pointed at the squares we generated from scratch. It opens the page. You didn't use a QR library. You became one.